Okay, guys, so in this video, we're going to take a look at a couple of more examples. So before I do that, I just have to change. I don't know what happens to my lined up paper. Anyway, so this is an example of solving this double integral of 3y dA over a region, let's call it D, and D is the region that is shaded here. So basically what happens is that this is just a region like a donut, whatever, but it's between two circles. So the outside circle has a radius of 4 and the inside circle has radius of 2. And so we want to integrate 3y over that specific region. Now, it's going to be very, very difficult to integrate it using x and y coordinates. Why is that? The problem is here is that when you're integrating with respect to x and y coordinates, you have to have a top curve and a bottom curve. But here, there's a problem. You will have to divide this into 3 different regions. So this would be like, say, region number 1. This is region number 2 over here. Well, this whole thing. And then this is region number 3. So number 1, the bottom curve, okay, would be like this. And then the top curve would be here. So that would be that square root of, I guess it would be like 4 squared minus x squared, because 4 is the radius. Now, on the next region, that 2, the bottom is going to be like all of that, right? That small circle. And then the top would be this circle, this part. And then finally on 3, then you will have this as a bottom and this is a top. So you have to like break it apart into 3 integrals and integrate each one, which I'm sure you do not want to do, right? But when you switch to polar coordinates, that's why I love them so much, is because any circular regions like this, it's so much easier to convert, because usually these integrals are going to be very easy to compute. So I'll show you that. So let's go ahead and start converting them. So what I'm doing is I'm converting to polar coordinates. Convert to polar. How do I do that? Well, I have to decide. So here is going to be my extra r, remember, because Pirate says r. So r d theta. Now, how does angle change? Well, angle starts over here at 0. And as we are traversing that region, if we're going to wind up over here, this is where the angle is going to be pi, right? So if you have the first and second quadrant, your theta, the angle, changes from 0 to pi. That's going to be your outside limits. The inside limits, okay, so now let's fix a theta. So let's fix some theta. So let's say theta is fixed, it's this angle. And then we wind up with, let me see if I can change it to another color here, like this dark green maybe. Okay, so this right here is what we're going to be integrating. So we're going to start over here. That's where the radius was 2. And then as we keep going over here, the radius will be 4. So this will go from 2 to 4. Okay, so we set it up. It's very easy. The limits don't have any variables. So, and actually this is going to be splittable into 2. So I'll show you that in a second. Okay, so anyway, we've got 3. And then we have y. Well, what is y? So remember we had a connection. So I told you that you need to know this, that x equals r cosine theta and y equals r sine theta. So what that tells you right there is instead of y, you're just going to put r sine theta. Now, why am I saying that this integral is splittable? Because I can go ahead and write the integrand, which is this right here, as a product of two functions. One will only have r in it and one will only have theta in it. So here we have 3r squared and we have sine theta, right? dr d theta. So it's splittable. This part is just the r part. It has no theta. And this part is the theta part. It has no r, right? And they are multiplied. So in that case, a double integral just becomes a product of two integrals. One is from 0 to pi of sine theta, and that's just a regular integral, multiplied by 0 to, oh, I'm sorry, that's not 0 to 4, I'm sorry. I made a mistake. This is supposed to be 2, right? Didn't I say 2 and then I said 0? Yeah, so you're right here from 2 to 4, right? Okay, so yeah, so it's good that I caught myself before I started getting deep into that. Okay, so this is going to be 2 and 4. And so this is going to be 3r squared. Oh, no, it's not going to be r squared either, because if you look at this term and that term, remember that extra r, that actually makes it into r cube. So this will become r cube. Okay, so now we just have to compute each of these integrals and multiply them, and we got it. So if you remember, hopefully, that integral of sine is a negative cosine, and that will be 0 to pi here. And then 3r cubed, that would be 3r to the fourth divided by 4. And we substitute r equals 2, and then r equals 4. So okay, so let's substitute first. So negative cosine pi. Now if you don't remember it, you can always go to Desmos, but cosine pi is actually -1. So that's going to be negative of -1, so that's going to be 1. And then we subtract what happens when we substitute 0. So I'm going to put it in parentheses. Well, cosine 0 is 1, but there is another negative here, so that will actually become -1. Okay, so multiply that by this guy right here. So this would be 3 multiplied by 4 to the fourth divided by 4 minus 3, 2 to the fourth divided by 4. Okay, so that's going to be equal to 1 plus 1. That's a 2. And whatever that whole thing is, I don't even know what it is. It's 3 times 4 cubed minus 3 times, well, 2 to the fourth is 16 over 4, so that would probably going to be 4. So anyway, you can compute that. I am just going to leave it, and you could just plug it into the calculator. Okay, one other thing that I wanted to just briefly show you, and then we're going to look at a couple of more examples in the next video, is what happens when we want to compute area of a circle. So hopefully everybody knows that that's pi r squared. But I can show you that very easily using polar coordinates, because it turns out that if you integrate using polar coordinates over some region, that will give you the area of the region. The question is, integrate what? Integrate 1. So if you are integrating over some region, if you're just integrating 1, so like there's nothing here, but I can put 1, I guess, if you want. That's just the area of region R. So if I were to integrate, let's say I want to know what's the, and here I'm just going to say that the radius of the circle is A, where A is some number. So I want to derive that formula for the area of the circle, right? So this is my circle right here with some radius A. So that's A. That's A right here. Okay, so let me set up the integration over the circle. So that should be really easy. First of all, theta would change from 0 to 2 pi because you are on the whole circle. And then the radius, so once you fix the theta, so you like, for example, from here to over here, your theta goes from 0 to 2 pi, and r will start at 0 and go all the way to a. So this would be like 0 to a. Now, I am integrating 1, that's true, but every time I convert to polar coordinates, remember that extra r that comes out, because that's what the pirate said, okay? So he told you to remember the extra r. All right, so this is a very easy integral. We're just going to separate it, split it into just the theta, which is, there's no theta, so it's just going to be d theta. And then 0 to a r dr. So this becomes theta, and we substitute 0 to pi. And then this becomes r squared over 2, substitute 0a. Okay, so what do we get? When we substitute 2 pi for theta, that'll be 2 pi. When we substitute 0, obviously that's just going to be 0. And then you multiply that by a squared divided by 2. So you get a squared divided by 2. And when you substitute 0, of course, that's just 0. Now notice how the 2 cancels out, and you wind up with pi a squared, which is the familiar formula for area of a circle, pi r squared. And so we just showed that, but that's true using polar coordinates.